This is the recording for practice questions 8, which I think, covers lecture 8 and 9. This is a long one, so hopefully we'll go through it quickly. And I have written some of the answers down already, so we'll just explain them quickly. And then some of these are kind of open-ended questions, so I encourage you to do also your own research. So go beyond the answers that I will provide now. I'm also, I think, trying to do different orientation for the recording. So I've been doing a vertical recording. I'm trying the horizontal now. Maybe it will be easier to watch, but let me know if you prefer that one. Okay, so the first one, what is your understanding of the relationship between a research problem, population samples, and sample data, and hypothesis testing? So first of all, when we have a research problem, there is usually a target population that is related to that research problem. Naturally, you have a target population. Then from the target population, you basically select the sample. From that sample, you start collecting the data that you're interested in, and then based on that sample data, you conduct your hypothesis testing, which allows the researcher to kind of make conclusions or make generalizations based on that sample data and basically try to answer the research question they have. So what is the logic of hypothesis testing? So the logic is basically comparing the sample data with the expected values. Basically when we define our null hypothesis, we have some expectations of what the sample mean is going to be. So in null hypothesis, you expect the sample to be the same as the population sample. And then in the alternative hypothesis, you expect the sample not to be equal to population sample. So basically you have these expectations of statistics of the sample data. So you want to compare the sample data of treated people, and you compare that to the population statistics. Question 3, identify the 4 steps of hypothesis test as presented in this chapter. So first is state your hypothesis, so stating your null and alternative hypothesis, and select an alpha level. Alpha usually is 0.05. And then locate the critical region. So based on this alpha, you locate the critical region based on basically alpha and the fact that are you doing a two-tailed or one-tailed test. You find this critical region. You collect the data and then compute the test statistics. And then basically based on that statistic, you make that probability-based decision about whether the null hypothesis is true or you want to reject that null. So question 4, does a hypothesis test allow a researcher to claim that an alternative hypothesis is true? Explain your answer. So this is referring to the case where we reject the null. So when you reject the null, it means that This means that, let's see, the mean of the sample of the treated people, so the sample that we collected the data from, is not close or like um, basically is beyond or in the critical region of the mean values. So you basically conclude that uh, the sample is not similar to the population. So we kind of, based on that, we make conclusions that the treated people are not the same as untreated people. So we kind of find this difference. But the thing is that uh, there is a lot of different factors when it comes to this difference. So this difference could be due to different factors. One of these factors is our treatment. So this different factors, one of them is treatment, but it could be other factors that have resulted in us rejecting the null. It could be like an error or different things. So to basically when reject the null doesn't automatically mean that all the difference that we had is due to the treatment. So we can't necessarily claim that the alternative hypothesis is true when we reject the null. So question 5, based on your understanding of the level of significance and critical region in hypothesis testing, when do you reject the null hypothesis? What are the circumstances that might lead to the null hypothesis not being rejected? Basically, based on the alpha level that we have, we define a critical region. This could be like a z-score. Basically, based on its alpha, we find a z-score that corresponds to that alpha level. So this we have a z-score that is equals to z1. So based on z1, we find the z1 in our distribution and then negative z1. So if the sample that we have is anywhere in this area or this area, we reject the null hypothesis. But if it is within these two bounds or within this kind of bigger portion of the distribution, we will retain the null. So basically, if our sample is large enough that is in this area or low enough that is within this area, it means that we reject the null. And then if it is within those thresholds, we will retain the null. But this is just an example distribution. The actual distribution would be a little bit different. So this is just an example. Okay, so basically these are the situations we would reject or retain null. What are the circumstances under which the possibility of type 1 and type 2 is most likely? So I wrote the short description or as a basically a review for what type 1 and type 2 error are. So type 1 error is when we have rejected the null hypothesis when it was actually true. So we should have basically retained the null, but we rejected the null by error, so that is type 1 error. And type 2 error is when we have not rejected the null, which is basically we retained the null, but we should have rejected it. So the null was actually false, but we made an error and we did not reject it. One of them, one of the main factors of that can influence the type 1 and type 2 error is the sensitivity or the alpha level. So if this alpha level is too high, means that this bound that I was talking about, let me do it with another color, means that if it is high, means that this bound gets closer to the center. So from both sides. So this means that our rejection area is larger, so we are more likely to reject the null. This makes it more likely for us to reject the null, so the rejection area gets larger, and we will be more likely to reject the null, which again, consequently, makes us more likely to make the error to reject the null by mistake. And then on the other side, if the alpha level is too low, this makes the rejection area very small. So let me see if I can do it here. So if our alpha level is too low, then this makes the rejection area smaller. So this will be the area that will reject the null. And therefore it will we are more likely to not reject the null because the rejection areas will be smaller. So these are how sensitivity can influence, and then we have the sample size. So if the sample size is too small, again we are less likely to reject the null. Since we might have like a not large enough sample to be able to confidently reject the null. This, I believe, has to do with a standard error. So I don't want to get into a lot of details, but this has to do with the standard error. So if our sample size is too small, then our sampling error will be too large. And then with a larger sampling error, then it'll be more difficult to reject the null. And then effect size, again, effect size basically means that what is the difference between, or how large is the effect of the treatment? Like what is the difference between the treated and the untreated groups? Like how much is this difference? Or like how large is the effect of the treatment that we are testing? So if the effect size is too small, again, we are less likely to be able to reject the null, because if the differences and the numbers are too small, then we are less likely to have a large enough number that would actually land here in the rejection area. Okay, question 7. Suppose the researchers is interested in the effect of a new college preparation course on scores for a standardized critical thinking test with a population mean of mu equals 20 students receive training in the course and later receive a standardized test. The researcher wants to test the hypothesis that the course affected test scores. So first, in words, to state the null and alternative hypothesis as they relate to the treatment in this example. So the null hypothesis is that the college preparation course um, um, does not affect the scores in critical thinking tests. You can word this differently as well. So you can say that the people who did go through the preparation course um, did not get a different score than people who took the course. So you can kind of word it differently, but this is the easiest way to uh, word it out. Let's see. I think we need to add significantly here as well. So the alternative hypothesis is that the college preparation course affect the scores in the test significantly. Then I just wrote the short type, but you can then add more details about like the critical thinking test or things like that. And then B is use symbols to say the null alternative hypothesis. So the null hypothesis means that the question gave us the mean for the population. So the null hypothesis is that the mean of the people or the sample who took the course will be the same as the population mean. So this tries to say that basically the course did not affect the mean of the sample. And this is how you describe the null hypothesis. And then for the alternative hypothesis, you write down that the sample mean is not equal to the population mean, and also it is not equal to 20. So the first one means that the sample mean is not significantly different from population mean, and that's how you write it. You just write equal, and then this means the sample mean is significantly different from population mean. Question A, what is your understanding of the alpha level and the critical region for the hypothesis test? So I kind of described this earlier. So as the alpha level increases, the critical region gets larger. So let's unpack this. What does this mean? So what does it mean to have an alpha level of 0.05? Let me. So basically, the simple meaning is that when we set the alpha level as 0.5, 0.05, it means that we are including only, or let me just, this, let's say this is a 0.5 alpha level. So we have this area as rejection areas. This is alpha, or like this is the alpha plus 0.05. So this means that the red area, this means that the red area includes 0.5 or includes 5% of the samples. So what we are basically saying is that this chunk in the middle, this is 95% of the sample. So we claim that the 95% of the data is actually in this middle section, and then the 0.5% or basically the 5% are, so basically 2.5% is here, and then 2.5% is here. So we basically are trying to say that these two areas, this and this area, they only consider 5% of the whole data or the samples. And what we do is if we find a sample which has the value here, so let's say we have a sample that has the mean that is here. This means that this sample, if it is in the critical region, we can say that there is less than 5% chance that this point, or this point basically here is a sample mean. So there is less than 5% chance that this point, or this basically sample mean, belongs to the sample that we have right now. But if it was somewhere in here, then since it is in the bigger chunk of the sample or bigger chunk of the distribution, then there is more chance for this point to belong to this sample than there is the other one. So that's when we claim that we have rejected the null, is basically where this sample mean is too far from the mean, that we claim that there is a very low probability that this is actually belongs to this distribution. So there might be another hypothetical distribution like this, that this point belongs to that distribution, which will be the distribution of the treatment population, basically. Hopefully this was clear. Let me know if you have questions on this. I know this is a little of a complicated subject. Okay. So question 9, define a type 1 and type 2 error and explain the consequences of each type of error, which is worse and why. So again, we kind of had this definition before. So the consequences of each one. So basically, for the type 1 error, we have rejected the null when we basically had to retain it. So this means that there was a treatment that was not effective, but we kind of mistakenly, but we claim that it is effective by error. So imagine there is like a medicine or something that we conclude based on our test that this medicine should be effective, but it it's not really effective. So the consequences of this is that we will be like using a lot of resources for like further researching that medicine or like even like doing like production or things like that. So it's a lot of like waste of resource, um, which is mainly why most people say that type 1 error is worse. And then the type 2 error, the consequence is basically we had a medicine that or we had a treatment that is actually effective, but we couldn't detect the effect basically. So this has also its consequences too, but it is the safer option between the two. So with the treatment, you can still do more experiments, do more testing to basically make sure that your first test was actually by error or not. Question 10, when the report of a hypothesis test reads that there was a significant effect, relationship or difference, and then reports the value of the test and the p-value, what does this mean to you? So kind of goes back to what we talked about here. When we report the test value, the test value is basically the value that basically corresponds to the sample you had. So basically the same way that we found like z-scores, you find the score for your sample compared to the mean value of sample means. So basically this shows that what is the number associated to your sample, and the p-value basically describes what is the probability. So the p-value is the probability of your sample basically belonging to the same population that was before the treatment. So the p-value is basically the probability. So here, for the next question, we will talk about this again. And then to kind of more talk about this more generally, when there is a significant effect, it means that we have rejected the null. And then there is like a significant effect. I hope this is what the question is referring to, at least. Okay. So when you read the following information in the report of hypothesis test, authoritative parenting had a significant effect on the prosocial behavior of adolescents with z equals 2.6 and p smaller than 0.05. What does it mean to you? So z equals 2.60. This means that the z-score for the sample you have, you are testing, is 2.60. This means that the sample you have is 2.6 standard deviation higher, or like they have higher prosocial behavior than the normal population. So, yeah, so like kind of conceptually, if you kind of think about like looking at a sample, the ones that have in a sample, the parents who had authoritative parenting, um, their children basically had 2.6 as standard deviation higher prosocial behavior compared to the rest. And then the p that is equal to 0.05 basically describes that there is, it is basically a similar thing that we talked about here. So this means basically there is less than 5% probability or chance that this basically this difference is just by chance. This is basically the p-value kind of describes that. Another way to also describe this is if we have our distribution and then we have the critical region that is again alpha equals 0.05, which is the same as we had here. This means that our p-value, the p-value that corresponds to each z-score is, so if this is the z-score 2.6 is here, this means the p-value that corresponds to the z-score is the p-value of the values that are larger than 2.6. So this p is smaller than 0.05 means that this area under the curve here, and then the one that we have on the other side here, sum of these two is smaller than 0.05, basically, which 0.05 was here. So yeah, so which also basically means that the z-score is higher than the critical z-score. Explain the factors that influence a hypothesis test. So first of all is mean differences. So when you're doing a hypothesis test, it matters what is the mean differences of the sample that you are looking at. So the mean of that sample compared to the population mean. So that is basically the mean differences. So it is important where within this distribution our sample is. Is it like here or here? So this basically is what the mean differences is talking about. So then variability of scores. So the variability of scores means basically the standard deviation of the population, I believe, which is important when we want to find. So if we have, if I write down the formula for the standard error for a sample, we can see that the standard deviation of our scores is important based on the formula. And then the sample size is also important. And then the mean difference is basically important because we want to see where within that distribution we are. This is again what we kind of described. So here, imagine we want to find the z-score of a sample. So we have a sample of size n. We want to find what is the z-score of the mean of that sample compared to all of the other samples. So for that, we can find the z-score of the mean of that sample minus m divided by why do we have that? Imagine we have the distribution of sample means. This is mu. We have the distribution of sample means, which is basically a distribution of what the sample means are for each sample, and then what is the distribution of them. We know that this mu for the mean for distribution of sample means is equal to mu or the mean of population. So now we have a new sample. We want to see how like different this sample is from the distribution of all the samples that we have, or like where within the distribution this sample lands on. So to find that where that sample is, basically we need to find the z-score of that sample compared to other samples. So here in this formula, let me write it larger so I can add more details around it. So z is m minus mu compared over sigma m. So this is basically the mean of the sample that we have. This is the population mean. Or basically, mean of sample means. It's like a lot of means, but so the mean of sample means is basically we find all the sample means. So for all of the samples, all possible samples, we find the mean for each of them, and then we find the mean of those means, which should be equal to the population mean as well. And then what we used to do for z-score, I'll just write down the old formula here too. What we did for z-score is that we would do this, right? We would do x minus m over a standard deviation. But here, since we're doing the distribution of sample means, the standard deviation of sample means is basically a standard error, right? So this is a standard deviation of sample means, which is technically also the standard error. So we're not doing anything differently, we're just using the same formula, but we are kind of changing how or what values we are using. Because technically a sample in a distribution of sample means is a data point within a distribution. So we're just looking at the distribution of sample means. And that is the difference. But we are technically doing the same thing. And then, so to find the z-score, we can see there are three different factors. One of them is the mean differences, which is basically, let me write it here because there's more space, is the m minus mu that we can see here too. And then the variability of the scores, which affects the standard error. Here, number 2. And then the sample size, again, influences the standard error. And then, so all of these kind of influences this z-score that we find. And then we use the z-score to kind of check whether our z-score is here in the rejection area or is in the retain area. Yeah. So question 14, explain the assumptions of hypothesis testing. The assumptions, you can read more about each of them. But first, random sampling. We already talked about that. Independent observations means that each observation that we do should be independent. For example, they should basically observations should not affect each other. So the third one is the standard deviation should remain constant after treatment. I don't know if you remember, but in the previous, I don't know, in the previous videos, we had a question that we basically added 2 points to all of the scores, and after adding those two, the standard deviation remained the same. So this is the same concept, because if we consider the treatment to have a constant effect on every participant, then sigma should remain constant after the treatment. And then using the appropriate test is kind of basic requirement. Differentiate between a directional and non-directional hypothesis. So directional is a hypothesis that has a specific direction for the effect. So if we specify that the effect that we want to see is increase in something or a decrease in something. So here, let's go back to that test question that we had. So here it says that the researcher is interested in the effect of the college preparation course. So if this specified that we are looking at whether this course can increase the critical thinking test. So here we had the test. So if we specify that the effect that we're looking at is either increase or decrease, that would be directional. But if we don't want to specify that, we by default will look at both increase and decrease directions. So if we don't specify and we're just like looking at any effect, which could be either increase, decrease, that would be non-directional. Why is it statistically right to always state and verify a two-tailed and not a one-tailed hypothesis? So again, the same with directional and non-directional. Directional hypothesis will require a one-tailed test, but the non-directional will require a two-tailed test. So if we go back here, directional might only look at this area. Let me use green or orange. So directional will either look at this area if it is a decrease, or this area if it is an increase. So this will be one direction, this will be the other direction. And this is why you call it one tail. So if we look at one of the tails of the distribution, it would be one tail. And then if we look at both tails, which would be non-directional. So with the two-tail test, we won't miss any effects. Because imagine, like for as we said, like we might be looking at increase or decrease. So it could be that we are looking at increase, but the effect that actually happens is a decrease and a significant decrease. While we were only looking at increase, we missed the decrease effect that was happening. But if we use the two-tail test, we won't miss any potential effects because we are looking at both sides. But with one-tail test, we can miss if there is a significant effect. in the other direction, basically. So we're looking at one direction, but there might be the significant effect on the other that we're missing. And then the last question, all scientific studies should have a hypothesis as stated and verified. How true is this statement? This is not true. Some studies might use qualitative approaches. Some of them they have smaller samples that you can't really do hypothesis testing. So this procedure is basically not for every research question.